Today we're going to look at some worked examples, but before I do that, I want to go over the formulas for calculating solubilities for different salts. Okay, if we have a 1-to-1 ratio such as silver chloride, which dissociates into silver ions and chloride ions, we can designate silver as X and chloride as X. This is the KSP expression, silver times chloride. And when each one of those is X, then KSP is X squared. X, which is the solubility, would therefore be the square root of the KSP. Okay, depending on what kind of calculator you have, you may have a square root function. If not, you can raise the KSP to the 0.5 power. Okay, let's consider next an example such as lead chloride, lead-2 chloride. This dissociates into a lead-2 ion and 2 chloride ions. Okay, so the KSP expression is lead 2 plus times chloride squared. And if we designate lead, for example, as X, then chloride would be 2X. Okay, so we would substitute X in for lead, 2X in for chloride, and notice we both double and square X for chloride. Okay, so combining terms, this becomes 4X cubed. Now to calculate solubility, we would divide the KSP by 4 first, and then we would take the cube root. We would do the same thing for a compound in a 2-to-1 ratio. This is a 1-to-2 ratio, such as silver sulfide. Okay, we would work it the same way. Okay, let's consider a 1-to-3 ratio. Okay, such as iron 3 hydroxide. This dissociates into iron 3 ions and hydroxide ions. And if we designate iron 3 as X, OH is 3X. Okay, we would substitute these values into the KSP expression. And 3 cubed is 27, so this becomes 27 times X to the 4th. We would then divide both sides by 27, and then take the 4th root, or you can raise it to the 0.25 power. This would work the same way if we had a 3-to-1 ratio for our compound. Okay, what about a 2-to-3 ratio? Okay, such as copper 2 phosphate. Okay, when this dissociates, we get 3 copper 2 ions and 2 phosphate ions. Okay, in this case, we would designate copper as 3X and phosphate as 2X. This is the expression for the KSP, as copper 2 is cubed, phosphate is squared. We would substitute 3X in for copper and 2X in for phosphate. So we would cube 3X and we would square 2X. Okay, combining all of our terms, this gives us 108 times X to the 5th. Okay, so we divide both sides by 108, and then we take the 5th root. Or you could take the answer to the 0.2 power. All right, next we'll look at some worked examples of aqueous equilibria. Okay, the first question is, write a balanced net ionic equation for the neutralization of equal molar amounts of nitric acid and the weak base methylamine, CH3NH2. Indicate whether the pH after neutralization is greater than, equal to, or less than 7. Okay, remember nitric is a strong acid. Okay, so the formulas that should appear in the net ionic equation depend on whether the acid and base are strong, completely dissociated, or weak, largely undissociated. The pH after neutralization depends on the acid-base properties of the cation and anion in the resulting salt solution. Okay, because nitric acid is a strong acid and methylamine is a weak base, the neutralization proceeds to completion, and the net ionic equation is hydronium plus methylamine produces water and the methylammonium ion. After neutralization, the solution contains CH3NH3+, which is a weak acid, and nitrate, which has no acidic or basic properties. Therefore, the solution is acidic and the pH is less than 7. Okay, next we'll look at calculating the effect of a common ion on concentrations, pH, and percent dissociation. The question is asking us to calculate the concentration of all species present, the pH, and the percent dissociation of ammonia in a solution that is 0.15 molar in ammonia and 0.45 molar in ammonium chloride. For comparison, the pH of a 0.15 molar ammonia solution that contains no ammonium chloride is 11.21, and the percent dissociation is 1.1%. Okay, so here are the steps in solving a problem like this. We would list the species present before dissociation and identify them as Bronsted-Lowry acids or bases. Then write balanced equations for all possible proton transfer reactions. Then we would identify the principal reaction, the reaction that has the largest equilibrium constant. Make a table that lists the following values for each of the species involved in the principal reaction: the initial concentration, the change, the equilibrium concentration, so in other words, an ice table, and we would define X as the concentration of the acid that dissociates. Okay, then we would substitute the equilibrium concentrations into the equilibrium equation for the principal reaction and solve for X. Then we would calculate the big concentrations, the concentrations of the species involved in the principal reaction. We would then use these big concentrations and the equilibrium equations for the subsidiary reactions to calculate the small concentrations, that is, the concentrations of the species involved in the subsidiary equilibria. Okay, the principal reaction is proton transfer to ammonia from water. Right, since ammonium ions come from both the NH4Cl initially present, which is 0.45 molar, and from the reaction of ammonia with water, the concentrations of all species involved in the principal reaction are as follows. Okay, so we have ammonia and instead of this term being 0, it's 0.45 because we've added the conjugate acid to the solution. Okay, so this will decrease by X. These will both increase by X. And we would substitute these values into the equilibrium constant expression. Okay, the expression would be NH4 plus times OH divided by ammonia. So this we would substitute in. Rather than X, it would be 0.45 plus X. Times X over 0.15 minus X. Okay, if we compare 0.45 to our Kb value, okay, we can assume that this x in the numerator, in parentheses, and this x in the denominator are both small and can be neglected. So our equation simplifies down to just 0.45 times x over 0.15. Okay, we assume that x is negligible compared to 0.45 and 0.15 because the equilibrium constant is small, and the equilibrium is going to be shifted to the left by the common ion effect. Okay, so when we solve for x is actually going to be the OH concentration. And that works out to 6.0 times 10 to the minus 6. Okay, and this is indeed much smaller than 0.15 and 0.45. Okay, so the ammonia concentration is really just what we started with, 0.15, and the ammonium concentration is again what we started with, 0.45. Okay, we can calculate hydronium by dividing Kw by our hydroxide, which is X, and that gives us 1.7 times 10 to the minus 9th. Okay, so the pH is 8.77. Okay, this is less than the pH of having just the 0.15 molar ammonia in solution. All right, the percent dissociation would be the X, okay, which we calculated. That was 6.0 times 10 to the minus 6. Okay, that is X, and that's divided by our initial, which is 0.15. Okay, we take that times 100%, and our percent dissociation is 4 times 10 to the minus 3rd. Okay, so we can see that the addition of all that ammonium, NH4 plus, suppress the ionization of ammonia. All right, so in this slide, we have a weak acid HA that also contains its sodium salt, NaA. The question is, which solution has the highest pH? And then which has the largest percent dissociation of HA? Sodium ions and water molecules have been omitted for clarity. Okay, highest pH would be the least acidic. Okay, so here in vessel 1, there is no dissociation of HA molecules. In vessel 2, okay, we have some of the molecules. It looks like 3 of them have been dissociated. And in this one, it looks like we have 1, 2, 3, 4, 5, 6 that have been dissociated. Okay, so the pH and percent dissociation are determined by the extent of the reaction. Okay, so 3 would represent the most dissociated. Okay, all 3 solutions contain the same number of HA molecules, but different numbers of A- anions. Okay, none for solution 1, 3 for solution 2, and 6 for solution 3. The dissociation equilibrium lies far to the left for solution 3. Therefore, solution 3 has the lowest hydronium concentration and the highest pH. For solution 1, no common ion is present to suppress the dissociation of HA. And therefore, solution 1 would have the highest percent dissociation. In this example, we'll be using the Henderson-Hasselbalch equation, also called the buffer equation. And let's calculate the pH of a buffer solution that is 0.45 molar in ammonium, NH4 plus, chloride, and 0.15 molar in ammonia. So how would you prepare an ammonia buffer that has a pH of 9? Okay, so this is the buffer equation down here. pH equals pKa plus the log of the base over the acid. Okay, so we would simply substitute our base, which is the ammonia, and our acid concentration, which is the NH4 plus, into this equation. Where do we get the 9.25? Okay, that's something we could look up in the tables. Actually, the Kb of ammonia is listed, and then we would have to calculate the pKb, and we can subtract that from 14 to get the pKa of ammonium. Okay, that's 9.25. And solving this equation, okay, this ratio, log of 0.15 over 0.45 is minus 0.48. So our pH is 8.77. Okay, for part B, again, we would use the Henderson-Hasselbalch equation. But this time, we know what the pH is. And what we would want to do is to solve for this ratio of base to acid. Okay, so we want to prepare a buffer of pH 9, and the pKa is 9.25, so we rearrange this. And the log of this ratio then comes out to negative 0.25. Okay, so to solve for this ratio, we would take 10 to the negative 0.25 power, so that would be 0.56. Okay, it doesn't actually specify what concentrations of these we need. They just need to be in the ratio of 0.56. So, for example, we could have 0.56 moles of ammonia and 1 mole of ammonium, or any other ratio that would, any other molar amounts or concentrations that would give us this ratio of 0.56. Okay, one of the things I hinted at when I first introduced the idea of preparing buffers was that when we prepare a buffer, we want this ratio of base to acid to be close to 1. Okay, and here we're going to calculate what ratio is required for a buffer solution that has a pH of 7. And then the next question is, why is a mixture of ammonia and ammonium a poor choice for having a buffer of pH 7? Okay, first we would calculate the required ammonia to ammonium ratio. Okay, this is just like the problem that we just worked. All right, so we would subtract the pKa from both sides, right? So 7, which is the pH we desire, minus 9.25. Okay, that's equal to negative 2.25. Okay, if we take 10 to the negative 2.25 power, we get 5.6 times 10 to the minus third. Okay, so that tells us that this ratio is very small, and this would be a really poor buffer. It would have little capacity to absorb added acid or base. And this ratio is far from 1, which is the ideal. And addition of a small amount of hydronium or hydroxide would result in a large change in pH. Okay, so if you're choosing a buffer of a desired pH, you want to go to the table and find a weak acid that has a pKa value that's close to the pH that you want. Okay, here we're going to calculate the pH of a diprotic acid strong base titration. Assume that you are titrating 30 milliliters of a 0.06 molar solution of the protonated form of the amino acid methionine, which we'll abbreviate as H2A+, with 0.09 molar sodium hydroxide. Calculate the pH after addition of the following volumes of 0.09 molar NaOH. Okay, here is the formula for protonated methionine. Okay, there's 2 acidic hydrogens. There's this one on the oxygen, and then there's this one on the nitrogen. Okay, so we have 2 Ka values, Ka1 and Ka2. Okay, so our strategy here is let's calculate the moles or millimoles of methionine solution that we started with. So we would take 30 times 0.06. And then for part A, we would calculate the millimoles of hydroxide that we added. And we could take 20 times 0.09, and that should actually give us the same number as our millimoles of acid that we calculated. Okay, so the number of millimoles of H2A plus present initially and the number of millimoles of NaOH added are 1.8 millimoles of acid initially, 1.8 millimoles of base added. Okay, and the added base is just enough to reach the first equivalence point. And so that would convert all of the H2A plus to HA, because the neutralization reaction would go 100%. Since HA is an amphoteric substance, calculating the pH is not complicated. In fact, this is an example of an equivalence point, which is an isoelectric pH. To calculate the isoelectric pH, we would take the average of the pKa1 and the pKa2 and divide by 2. Or we would take the average of those two, I should say. Okay, so on the previous slide here, we have the Ka values. Okay, so we would take minus the log of each one of those to get the pKa values. Now it turns out that it does not work if you take the average of these and then you take minus the log. You get the wrong answer. Okay, you have to take minus the log first and then take the average. Okay, so that's 5.74. Let's look at part B. Okay, here the amount of NaOH added to the 1.8 millimoles of H2A plus initially is 30 times 0.09. Okay, so that's 2.7 millimoles altogether. The added base is enough to convert all of the H2A plus to 1.8 millimoles of HA, and then convert half of the resulting HA to 0.9 millimoles of A minus because of the neutralization reaction. So after neutralization, we have an HA A minus buffer that contains equal amounts of HA and A minus. So in other words, we're at the halfway point between the two equivalence points. And at this point, our log term would become 0 and pH equals pKa2, which is 9.21. For part C, the amount of sodium hydroxide added to the 1.8 millimoles of H2A present initially is 35 milliliters times 0.09 millimoles per milliliter. So that's 3.15 millimoles. All right, the added base is enough to convert all of the H2A plus to 1.8 millimoles of HA, and then convert 3.15 minus 1.80, which is equal to 1.35 millimoles of the resulting HA to 1.35 millimoles of HA minus. So after neutralization, we have an HA A minus buffer solution that contains 0.45 millimoles of HA and 1.35 millimoles of A minus. Okay, so we can plug those values into the Henderson-Hasselbalch equation and calculate the pH. We're in the buffer region, but we're not at the halfway point. So this log term doesn't drop off to 0. So that would be 9.69. Okay, because the conjugate base predominates in part C, the pH should be greater than pKa2 in agreement with the solution. Also note that the pH increases as the NaOH is added. Right, I'm going to stop at this point, and in the next lesson we'll look at KSP calculations.